Welcome to the fourth week of this discrete mathematics course. So till now we have been looking at various proof techniques and we have looked at some of the most interesting proof techniques, namely direct proofs, proof by contradiction and proof by contrapositiveness. In this week and in the next week we will be looking at one of the most powerful proof technique that is available to us in this field of discrete mathematics, namely induction. So quickly to recap, to prove a statement like A implies B, there are different kind of proof techniques. Constructive proof, proof by contradiction, proof by contrapositive, induction, counterexample, existential proof, and so on. We have till now looked at some of the proof techniques. So this is something that I have told you again and again, but I will repeat it all once more time. Namely, given a problem, which proof technique to apply? Now there is no fixed rule about that. Which proof technique to apply depends upon the problem and your understanding of the subject. So there are some problems that can be split into smaller problems that can be easier to handle. While for some problems, one can view the problem in a slightly different way, which can make the problem easy. But how to split a problem and when to split a problem, or when to look at it in a different way, all of this depends upon your understanding of this subject. It's an art that has to be developed. There are some thumb rules which we have been discussing and which we will keep on continue to discuss. But in the end of the day, you have to decide which rules to apply for which problem. Now till now, we have seen a few simple tricks that can be applied. To start with, we looked at how to split a problem into smaller parts. If when to prove A implies B, B can be written as C and D. In that case, it can be split into A implies C and A implies D. Each of them can be solved individually and hence making it into slightly easier problems. The second option is removing some kind of a redundancy in the assumptions. Namely, if A implies B, and that would imply that A and any other assumption will also imply B. So if the given set of assumptions is A and C, one might want to remove the redundant assumptions, and that would make this problem easier, neater, and hence easier to solve. The third interesting trick is that sometimes proving something stronger can actually be easier. Namely, if you have to prove A implies B, but we know that C implies B, and it might be the case that A implies C is easier to prove than A implies B. And in that case, one would like to solve the A implies C instead of A implies B, although A implies C is a stronger statement than A implies B. Other than these three tricks for solving problems, we also looked at some of the proof techniques. In particular, we looked at the direct proof technique. The idea is that to prove A implies B, we start with an assumption A and step by step prove B. But sometimes getting such a proof can be magical and hence difficult to understand how to obtain. So there is another technique for attacking this problem in this form, namely going via a backward proof. Or in other words, to prove A implies B, start with B, simplify it. Now if you can simplify B to something called C, then A implies B is same as proving A implies C, and in that case A implies C can be easier to prove. So this is called the constructive proof or direct proof. There is one more technique which is also a part of the constructive proof, which we call case studies. The idea is that if you can split up the assumptions into a finite number of cases, then you can solve them in a case by case basis. So thus, if you can write A as C or D, then A implies B is same as proving C implies B and D implies B. So that is gets split into two smaller problems depending on the cases. Again, how to break up the assumptions into cases, of course, depend upon the problem itself. We have seen quite a number of examples in this regard. The third technique that we have seen is what we call a proof by contradiction. The main idea is that to prove A implies B, one can also prove not B and A is false. A very similar statement is also not B implies not A. So this is called the proof by contradictiveness. Here, if B, that is the deduction, can be written in the form of C or D, then A implies B, one can apply the proof by contrapositiveness and get a statement of the form not C and not D implies not A, which would be an easier technique to prove or easier problem to prove. Now, proof by contradiction and proof by contrapositive, we have spent again a week on this particular two techniques, and these are very powerful techniques for problem solving. So this helps us to view the problem in a slightly different way, which is possibly easier to attack. The one more thing that we have looked at is what we call a proof by counter example. Namely, if we have to check whether the statement A implies B is true or not, and particularly if the problem is of the form for all x, Ax implies Bx, where Ax and Bx are two predicates, then to prove that this is not true, we have to prove that the negation of this one is true. Or in other words, we have to prove that there exists an x where Ax doesn't imply Bx. And by usual assumptions or usual deductions, namely A implies B is same as B or not A, we can replace this there exists x, Ax not implies Bx as there exists x, not Bx and Ax. So thus, to prove a statement A implies B is not true, I have to find an x which does not satisfy Bx but satisfies Ax. And this is called the proof by counterexample. Now, all these various proof techniques that we have done are actually proof techniques that can be applied to any field of math, not particularly discrete math. Meaning this can be applied to discrete math, continuous math, or any logical set of statements. But the next proof technique that we are going to see is something that can be applied to only discrete objects, and hence a very unique proof technique. And we will very soon see it's one of the most powerful proof techniques that we have. We call it as induction. So the main idea is that sometimes the set of assumptions or the conditions for which it should be true, or the objects for which we have to prove the theorem, they can be split up into infinite but countably many subsets. So in other words, when proving A implies B, we can split A as, or this whole problem as, and of infinitely many problems. So these sub-problems are indexed by some parameter of the input. So in other words, I would like to write A implies B as P1 and P2 and so on till Pn and so on. So I made a mistake in the slide here. These are all should be AND. So P1 and P2 and P3 and dot dot till Pn. Okay. Let's look at an example. So consider this problem like for all n greater than or equal to 1, we want to prove that 1 plus 2 plus dot dot till n is n into n plus 1 by 2. Now how do you prove it and what are the smaller statements? Now let me define pk to be this particular statement 1 plus 2 plus up to k equals to k into k plus 1. So the problem statement can be restated as for all k greater than 1, prove that pk is true. So here the pk's are the subproblems. Right? So the original problem has been broken up as AND of infinitely many problems, namely the pk's. Note that usually this is how we end up doing. There is a natural parameter. For example, here it was this n, through using which we split up the problem into smaller problems. When we can split up the problem into smaller problems, we usually say we are inducting on this particular parameter. So in this problem, we will be inducting on n. Let's look at a second example. Say for all n greater than or equal to 1, prove that 11 divides 23n minus 1. Now, can you guess what are the PIs? So let's define it by again using n as the parameter. So in other words, pk is 11 divides, so sorry again I made a mistake here, 23, this should be 23k plus 1. So 11 divides 23k plus 1. So the problem can be restated as for all k, prove that pk is true. So again I broke this original problem into infinitely many problems, each parameterized by an integer, namely here k. Now let's try to understand how to break up one more problem. So here is a slightly more complicated problem. You have seen this problem maybe earlier. This is called the AMGM inequality. This says that for all n and for all positive real numbers a1 to an, we have a1 plus a2 plus dot 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 till an by n. That means the average of a1 to an is greater than or equal to the nth root of the product of ai's. Nth root of a1 times a2 times dot dot till n. Now again here, what are the pk's? So here there are possibly many parameters, right? For example, there are the ai's, there is the n, so there is a lot of parameters. There can be multiple ways of breaking up a problem into smaller problems, and almost all these techniques can lead to a solution. So some of them might be easier or harder. In this problem, let me break it up into this following way again. This says that let pk be such that for all positive real numbers a1 to ak, the average of a1 to ak is greater than the kth root of the product. And since the original problem says that we have to prove it for all n, so this statement boils down to proving that for all k greater than or equal to 1, prove pk is true. So this is another example of breaking up the whole problem into smaller problems. This is something extremely important as the first step of induction. As I told you, the induction starts with breaking up the problem or the assumptions into infinitely many sub-problems parameterized by some integer which is some kind of a property of the input. Now, what do I do after that? I cannot apply things like just proving for all the different PIs. So, for example, if I have to prove that for all k greater than or equal to I, prove that pk is true, there are infinitely many subproblems, and one cannot expect to solve all the subproblems. So, how do we go about it? So, the idea is that first proof P1 is true. That is something you have to prove. And next, assuming that I have managed to prove Pk is true for some Pk, for some k, prove that Pk plus 1 is true. And by doing so, I should be able to have convinced you that for all n, this number Pn is true. Hence, proof. Just a quick remark. We have already seen in the beginning of this set of proof techniques that if the A can be broken up, or particularly in the case study problem, if the A can be broken up into finite number of parts, the problem breaks up into finite number of or constant number of subproblems, and we solve each of them together one by one. Each of them one by one. But here, since there are infinitely many subproblems, we cannot do such thing. So this seems to be a pretty natural way of doing it. Though, I must tell you that whether this actually ends up proving all for the all n or not has some bit weirdity. Namely, assuming I cannot prove using the propositional logic or predicate logic that this statement will end up proving the whole problem. So usually what we do is that we call this one the principle of mathematical induction. It's an axiom in math which says that if for any predicate, for any problem, if I can first prove P1 and then for all k, if I can prove Pk implies Pk plus 1, then this implies that for all k I have proved Pk. So this is an axiom in the mathematical framework, and one might tend to argue whether this axiom is right or wrong, but there are a lot of mathematicians who accept this one as a reasonable axiom, meaning this statement is true. So this is an axiom, and this we call as a principle of mathematical induction. So using this principle of mathematical induction, we can now have a technique of proving this infinitely many collection of subproblems. So to prove this statement that for all k greater than or equal to 1, prove that Pk is true, there are three parts to it. The first part is what is called the base case, where you prove P1 is true. The second part is called the induction hypothesis, where we assume that we know Pk is true for some k greater than or equal to 1. And the inductive step is that, assuming the induction hypothesis, can you prove the next statement, namely, can you prove Pk plus 1 is true? So these are the three steps that are there. So step 1, step 2, and step 3. And once you have the step 3, then it follows that I have the whole problem. Namely, we have proved that for all n, Pn is true. This is what is guaranteed by the principle of induction hypothesis, and we will be using this one to prove our theorems or our problems. So let's look at this first problem. So the problem was that for all n, prove that the sum of the n numbers, first n integer, is n into n plus 1 by 2. Now I have split up this problem into sub-problems, namely where pk is the sum of first k object, k integer is k into k plus 1 by 2. And the main problem boils down to proving that for all k, this statement is true. Now let's use the principle of mathematical induction. So what should be done? So first of all, so this is the pk, namely sum of the first k element is k into k plus 1 by 2. We have to first prove base case, which is that p1 is true. We have to assume the induction hypothesis. So that means for some k, pk is true, and we have to prove that the inductive step that assuming pk is true, prove pk plus 1 is true. This is a very simple kind of a step-by-step way of proving a problem. Now let's put these numbers back. So what does this base case turn out to be? So it was p1 is true, or in other words, the first element 1 is equals to 1 into 1 plus 1, which is 2 by 2. And this is indeed true. Now inductive hypothesis says that for all k, I have to prove that pk is true. For some k, we have assumed pk is true. So let's assume that 1 plus 1 till k, the first k element, integers add up to k into k plus 1 by 2. And the inductive step says that assuming the inductive hypothesis proves that the first k plus 1 number is k plus 1 into k plus 2 by 2. As you can see, this whole problem has been boiled down to some 3 basic steps. So let's do the first step to prove that the base case is true. Now, as you can see, this particular case is very obvious here, because 1 into 2 by 2 is actually 1, which is obviously true. Okay, so the induction hypothesis is, let for some k, the sum of the k element integers is k into k plus 1 by 2. And the inductive step, we know what to do. So now let's try to prove it. Now we have to prove that the sum of the first k plus 1 element is something. So first of all, note that the sum of the first k plus 1 integers is sum of the first k integers plus k plus 1. Now by induction hypothesis, we know that the sum of the first k integers is k into k plus 1 by 2. So we can plug it in and we get that. So the sum of the first k plus 1 integers is k into k plus 1 by 2. And if you now just do the calculation here, you get that this is actually equals to k plus 1 plus k plus 2 by 2, which is what we wanted to prove. So thus we have proved the inductive step. So while this original problem might have looked a bit daunting, namely how do you prove that in sum of any first n number of integers is n into n plus 1 by 2, the principle of mathematical induction gives us a way to solve it by following 3 basic steps: base case, induction hypothesis, and inductive step. So we have proved this following problem, and I would ask you guys to try to come up with solutions to this problem without using mathematical induction. In this case, it is doable, though a bit tricky. In the coming week and next week, we will be looking at various variants of mathematical induction and how to use it to solve different kind of problems. Thank you.